The damaged bomber sat motionless under the scorching Java sun. February 8, 1942 had been a day of chaos and retreat. American crews abandoned their aircraft as Japanese forces swept across the island. This particular Boeing B-17E bore serial number 412471. Its crew had vanished hours before Japanese soldiers reached Jakarta airfield. The aircraft belonged to America's 7th Bomb Group. Despite crash damage during landing, the fortress remained surprisingly complete. Enemy forces would soon discover this prize, along with similar bombers scattered throughout Java's airfields. These abandoned aircraft would shatter Japanese assumptions about American manufacturing. The bombers represented far more than abandoned military equipment. They embodied production philosophies that contradicted everything Japanese industry practiced. Japanese engineers would spend 3 years dissecting these machines. Their discoveries would devastate confidence in Japan's ability to match American industrial output. March 1942 brought systematic examination as Japanese conquest of the Dutch East Indies reached completion. Engineers at Madoan Field discovered the remarkably preserved B-17E, despite missing nose section and engines. Additional bombers awaited discovery at neighboring airstrips in various damaged states. Aviation editor Torao Saito from Asahi Press toured captured bases immediately following Japanese occupation. His documentation revealed 4 B-17Es prepared for detailed study. Malang held one example. Cirebon contained another. Bandung housed 2 additional aircraft. The B-17 maintenance capabilities in Java impressed Saito with their sophistication for wartime conditions. Bandung Field appeared to serve as the primary American maintenance hub. Japanese technicians from the prestigious Giken conducted initial assessments here. The Koku Gijutsu Kankujo represented Japan's pinnacle aeronautical research organization. This Air Technical Research Institute operated from Tajikawa Airfield near Tokyo. Japan's most brilliant aircraft designers and engineers worked within these facilities. Word of intact B-17 discoveries prompted immediate technical team deployment to Java. Preparing captured aircraft for evaluation presented enormous challenges. The B-17E represented the most advanced American bomber variant deployed to Pacific operations. Its systems exceeded Japanese inventory complexity by significant margins. Engineers salvaged components from multiple damaged aircraft while pressing captured Allied mechanics into service. The painstaking restoration work demanded months of concentrated effort. Understanding electrical systems required completely new approaches. Hydraulic installations differed fundamentally from Japanese designs. Engine systems presented unfamiliar engineering solutions. Captured instruction manuals provided essential guidance as teams translated technical documentation. American engineering practices demanded careful study and interpretation. Late 1942 witnessed successful restoration of 2 airworthy B-17Es. A third aircraft, a B-17D from Clark Field, Philippines, had already reached Japan earlier that year. Transportation plans required elaborate coordination for moving restored Java bombers to Japan. The journey would span thousands of miles over recently conquered territories. Singapore provided the first major waypoint northward to Japan. Extensive flight planning prevented Japanese air defenses from destroying their own captured prizes. Fighter escorts received detailed briefing. A Nakajima L-2D transport would accompany the bombers as mothership support. Every air defense position along the route received advance warning notifications. May or June 1943 brought successful arrival of both B-17Es at Tachikawa Airfield near Tokyo. They joined the earlier Philippine B-17D for comprehensive examination. Japanese engineers now possessed 3 examples of America's primary heavy bomber. Major Kazuyuki Saito led the Imperial Japanese Army Air Force evaluation team at Tachikawa. This accomplished aeronautical engineer possessed extensive aircraft design and testing experience. His assembled specialist team included Lieutenant Shiyama and Lieutenant Second Class Karusu and O'Hara. Army Assistant Engineer Shima Mura provided additional expertise. Major Uno and Captain Yagi served as designated test pilots. Army Engineer Kanako focused specifically on engines and propulsion systems. The team's mission was absolutely clear. Document every design aspect, construction detail, and operational capability. Complete instruction manual capture meant no detail would escape examination. Every system faced testing. Every component demanded analysis. Every manufacturing technique required documentation. Airframe structure examination began the comprehensive process. Construction methods received careful documentation as engineers measured rivet spacing, panel thickness, and structural dimensions. Their discoveries immediately challenged American manufacturing assumptions. Construction consistency across all three aircraft proved remarkable beyond Japanese experience. Rivet hole alignment matched precisely between different aircraft. Structural components appeared completely interchangeable without modification. Panel forming showed identical characteristics across multiple examples. This was not individual craftsman work adapting parts to specific aircraft. This represented systematic mass production using standardized components manufactured to precise tolerances. Japanese aircraft production depended heavily on skilled workers fitting components individually to each airframe. No two Japanese aircraft achieved true identity. Parts from one aircraft typically required adjustment before fitting another machine. Field repairs demanded skilled technicians who could modify replacement parts to match specific aircraft requirements. American approaches appeared fundamentally different from Japanese methods. B17 construction suggested any specification part would fit any same-model aircraft without adjustment. This standardization level required manufacturing precision Japanese factories had never achieved. Engine examination provided even more dramatic evidence of American mass production capabilities. Wright R-1820 Cyclone radial engines powering B-17s contained hundreds of precisely machined components. Engineers completely disassembled engines while measuring clearances and tolerances throughout. Their findings proved astonishing as every component showed machining to tolerances measured in thousandths of an inch. Crankshafts, connecting rods, cylinder barrels, and pistons displayed identical dimensions across different engines. Maintenance manuals confirmed physical examination suggestions. American field mechanics expected to replace major engine components without fitting or adjustment procedures. Any cylinder from one engine would install directly into another engine without modification. Crankshaft interchangeability meant precisely identical replacement without adjustment. This contrasted starkly with Japanese engine production methods. Japanese aircraft engines required skilled technician assembly with extensive hand-fitting to achieve proper clearances. Field maintenance demanded highly trained mechanics who understood component adjustment and modification techniques. American systems eliminated specialized skill requirements by building precision into manufacturing processes rather than depending on craftsman expertise. Hydraulic system examination demonstrated identical principles throughout the aircraft. Engineers examined actuators, valves, and control mechanisms systematically. Fittings used standardized threads exclusively. Lines connected with identical couplings throughout entire systems. Any hydraulic component allowed removal and replacement without modification requirements. Electrical systems showed even more sophisticated standardization approaches. Every wire connection used machine-crimped terminals rather than hand-soldered joints. Wire gauges followed consistent standards throughout aircraft installations. Circuit breakers, switches, and instruments appeared as modular units designed for quick replacement. Japanese aircraft electrical systems typically required skilled electricians capable of soldering connections, adjusting contacts, and troubleshooting complex wiring installations. B-17 electrical systems were designed so basic trained mechanics could replace entire assemblies using simple tools. Crew oxygen systems included precision regulators controlling flow to each crew position. Japanese aircraft regulators required assembly by highly trained specialists. B-17 regulators bore manufacturer stamps, indicating automobile parts, supplier production by companies lacking prior aircraft experience. This discovery carried profound implications for industrial assessment. American industry possessed such manufacturing depth that automobile parts manufacturers could produce precision aircraft components by applying existing capabilities to new products. Bomb release mechanisms told similar standardization stories. Japanese bomb racks required careful adjustment by armament specialists. B-17 bomb shackles were self-adjusting mechanical devices requiring no calibration procedures. Defensive armament particularly impressed Japanese fighter pilots conducting practice intercepts against captured bombers. 13 Browning M2 50-caliber machine guns provided overlapping fire fields covering virtually every approach angle. Each gun could fire up to 600 rounds per minute sustained. The weapons themselves revealed another American design philosophy aspect. Engineers examining guns found them surprisingly crude in construction with loose tolerances compared to Japanese aircraft weapons. Yet they functioned reliably, despite what Japanese engineers considered rough manufacturing approaches. Design achieved reliability through robust engineering rather than precision craftsmanship. Any competent armorer could maintain weapons using simple tools and basic training levels. Japanese aircraft guns were precision instruments requiring skilled maintenance procedures. American guns were robust mechanisms designed to function despite imperfect operational conditions. Autumn 1943 brought regular flight operations for all three captured B-17s from Fusa Airfield near Tachikawa. Japanese pilots gained first-hand heavy bomber operational experience. Test flights documented performance characteristics, handling qualities, and operational procedures systematically. Aircraft appeared in Japanese military training films demonstrating combat tactics for intercepting American heavy bombers. Films showed Ki-43 and Ki-44 fighters practicing attack procedures against captured B-17s. These productions sometimes featured the B-17D repainted with American insignia and occasionally escorted by captured Curtiss P-40 fighters for additional realism. Films played in Japanese public theaters as propaganda showing Japanese fighters successfully engaging American bombers. What propaganda films never showed were sobering conclusions Japanese fighter pilots reached after extensive practice intercepts. Even when Japanese fighters successfully attacked bombers, B-17 defensive firepower and structural strength made them formidable opponents. More disturbing was the realization that for every B-17 destroyed, American factories would produce replacements faster than Japanese industry could replace lost fighters. February 1943 brought comprehensive analysis publication by Asahi Press titled Anatomy of the Enemy's Aircraft. This publication featured extensive captured Allied aircraft analysis with special B-17 attention. Photographs displayed every major component in detail. Technical drawings illustrated critical systems comprehensively. Specifications filled page after page with measurements and capabilities. This book became required reading for Japanese aircraft engineers throughout the industry. Mitsubishi engineer Hisanojo Ozawa, designer of Ki-21 and Ki-67 twin-engine bombers, contributed B-17 analysis for May 1942 Koku Asahi Aviation magazine. Ozawa's analysis proved revealing in acknowledged facts and carefully avoided direct statements. He noted B-17E represented modifications to designs first flying in 1935, suggesting aircraft were based on outdated concepts. Martin B-10s and Handley Page Harrows of similar vintage had been phased from service, Ozawa observed. Yet he admitted improvements had made B-17's first-line combat aircraft, and original designs had been extremely good. Another Japanese aviation expert, Shizuro Kikuhara, designer of four-engine Kawanishi H-8K flying boats, examined captured B-17s and commented on most impressive findings. American engineers have perfected bomber subsystems to such degrees that minimum controls are needed in cockpits, he wrote. Cockpit arrangement, simplicity, considering aircraft size, demonstrated sophisticated systems integration achievements. Published analyses carefully avoided stating explicitly the most disturbing conclusion reached through examination. B-17 construction methods represented industrial organization levels. Japanese factories could not match. Aircraft were not superior because of better aerodynamic design or more powerful engines. They were superior because American industry could produce them in quantities overwhelming Japanese air defenses through sheer numbers alone. Examination revealed B-17 construction in extensive detail previously unknown to Japanese engineers. Wing panels were stamped from dies rather than hand-formed over wooden forms. This required massive hydraulic presses and precision dies costing fortunes to produce initially. But once dies existed, workers could stamp panels by hundreds per day. Control surfaces showed identical forming techniques throughout. Every aileron, elevator, and rudder section appeared produced from master tooling rather than individually crafted by skilled workers. Main wing spars, critical structural members carrying flight loads, were machined on automated equipment with consistent precision. Drilling patterns matched exactly across multiple aircraft examples examined. Any wing rib from one bomber would fit precisely into another aircraft of identical model without adjustment. Landing gear demonstrated automated precision machining throughout components. Main struts were forged components that were heat-treated and machined on automated lathes. Actuating mechanisms consisted of hardened components machined to identical specifications across different aircraft. Early 1944 brought destructive opportunity when one captured B-17E was damaged beyond repair in a ground accident. During takeoff from Fusa Airfield, the aircraft was caught in unexpected crosswinds. Its right wing collided with a parked Ki-49 bomber during ground operations. Both aircraft were destroyed in the collision. This incident provided opportunity for destructive examination previously impossible. Engineers could cut into damaged wing structure to examine construction details not visible in intact aircraft. Cutting through wing skin and structure allowed engineers to measure rivet installation with unprecedented precision. Hundreds of rivets were measured individually for consistency. Diameter variation proved minimal at less than 2/1000ths of an inch. Installation depth varied by less than 1/1000th of an inch across the entire wing structure. Such consistency across thousands of rivets was impossible to achieve through hand riveting techniques. Aircraft had clearly been assembled using automated or semi-automated riveting equipment. These implications extended beyond immediate questions of how one aircraft was built to broader industrial capabilities. If American factories could produce B-17s with this consistency level, they could produce them rapidly in large quantities. If parts were truly interchangeable, field maintenance became dramatically simpler for less skilled personnel. If workers needed less skill because precision was built into tooling rather than craftsmen, production could scale up quickly by training new workers rather than developing skilled craftsmen over years. Japanese aircraft production faced exactly opposite situations in every aspect. Skilled craftsmen remained in perpetual short supply throughout the war. Training new workers to required skill levels took years of careful instruction. Increasing production meant finding and training more skilled workers rather than simply adding more assembly stations with less skilled personnel. May 1945 brought puzzling American photographic reconnaissance over Tachikawa Airfield, capturing images that confused intelligence analysts. Clearly visible was what appeared to be a new type of Japanese four-engine bomber or transport aircraft. Analysts estimated aircraft wingspan at approximately 104 feet, based on photographic measurements. This mysterious aircraft was designated Tachikawa 104 based on estimated wingspan and its airfield location. Weeks passed without additional information as speculation grew about Japan's apparent development of new heavy aircraft despite intensive bombing of Japanese aircraft factories. None of the American analysts examining photographs suspected the actual truth. The mysterious aircraft was actually one of their own B-17E flying fortresses, still undergoing evaluation by Japanese engineers 4 years after initial capture. Actual B-17 wingspan measured 103 feet 9 inches, making American intelligence estimates remarkably accurate, despite misidentification. Extensive B-17 evaluation had surprisingly little impact on Japanese bomber design development. Japan attempted copying the Douglas DC-4E transport as the Nakajima G5N bomber with limited success. Its other four-engine land-based bomber, the Nakajima G8N entering production near war's end, used more advanced structural designs, gaining nothing from B-17 airframe engineering lessons. Evidence exists, however, that B-17 components and systems influenced later Japanese aircraft development attempts. Most notable were attempts to perfect turbo-superchargers for high-altitude performance capabilities. Several advanced Japanese designs, including Army's Tachikawa Ki-74, Mitsubishi Ki-83, and Nakajima Ki-87, as well as Navy's G8N and Mitsubishi J2M, failed to reach full potential, mainly because Japan could not successfully implement turbo-supercharger technology. The problem was not understanding technology principles. Japanese engineers examining B-17s understood how turbo-superchargers worked in theory and practice. The problem was manufacturing implementation. Turbo-superchargers required high-temperature alloys, and precision manufacturing Japanese industry could not consistently produce at scale. Even when experimental units were built successfully, they proved unreliable in operational conditions. Same manufacturing limitations preventing mass production of standardized B-17 components prevented development of advanced engine technologies. By 1944, cumulative evidence from examining captured American aircraft had led thoughtful Japanese engineers to sobering conclusions about relative industrial capabilities. American aircraft production reached 96,000 aircraft in 1944 alone. Japan struggled to produce 28,000 aircraft the same year. But disparity in numbers understated the real capability gap significantly. American aircraft consisted of thousands of precisely manufactured, interchangeable parts, enabling simplified maintenance. They could be maintained by mechanics with basic training using standardized replacement components available through supply systems. They could be repaired in field conditions quickly and returned to service. Japanese aircraft remained craftsman-built machines requiring skilled technicians for maintenance, specialized parts for repairs, and constant adjustment to remain operational. Each American aircraft represented greater actual combat capability because it could be kept flying with less effort and fewer specialized resources. Production systems enabling this output were visible in B-17 construction methods. Boeing's Plant 2 in Seattle had produced 6,981 B-17s by production end in April 1945. At peak production periods, 16 complete B-17s rolled off assembly lines every day. Douglas Aircraft in Long Beach produced 3,000 B-17s between July 1942 and July 1945. Lockheed Vega in Burbank built 2,050 B-17s between August 1942 and August 1945. Total B-17 production reached 12,131 aircraft from all three manufacturers combined. Japanese engineers examining captured B-17s in 1943 and 1944 had no access to these production statistics, but they could calculate approximate production rates based on observed serial numbers and construction dates documented in aircraft records. The mathematics proved devastating to Japanese confidence. If American factories could build B-17s with such precision and consistency, they could build them rapidly in enormous quantities. If they could build heavy bombers this quickly, their production of fighters and other aircraft must be proportionally greater. Japan had entered a war of industrial attrition against an opponent with 10 or 20 times its manufacturing capacity. Strategic bombing campaigns against Japan's aircraft industry, intensifying in 1944, destroyed any remaining hope for matching American production levels. Boeing B-29 superfortresses, the B-17's larger and more advanced successors, appeared over Japan in formations Japanese defenses could not stop. Each raid destroyed production capacity that could not be replaced under wartime conditions. Nakajima Plant at Musashino, Mitsubishi facilities at Nagoya, and Kawasaki factories all suffered severe damage from precision bombing campaigns. An earthquake in January 1945 compounded damage to Mitsubishi's supplier networks. The combination of bombing and earthquake collapsed Japanese aircraft production capabilities. By early 1945, monthly output had fallen from over 2,500 airframes in May 1944 to barely 1,500 per month. Decline continued through the final months of war until surrender. After Japan's surrender in August 1945, United States Strategic Bombing Survey conducted comprehensive examinations of Japanese war production capabilities. Teams of American engineers toured Japanese aircraft factories, documenting production methods and assessing industrial capabilities systematically. What they found confirmed conclusions perceptive Japanese engineers had reached through examining captured B-17s. Japanese aircraft production relied heavily on skilled manual labor throughout manufacturing processes. Standardization remained limited across most industry sectors. Interchangeable parts were more aspiration than reality across much of the production base. Subcontracting networks provided components, but quality control and dimensional consistency proved problematic. American engineers touring Mitsubishi facilities at Nagoya observed skilled craftsmen hand-forming aluminum panels that would have been die-stamped in American factories. Manual riveting predominated where American factories used automated riveters. Individual fitting and adjustment were common where American factories used precision, manufactured interchangeable parts. The survey concluded Japanese aircraft factories had been organized appropriately for producing hundreds of aircraft. American factories had been organized for producing hundreds of thousands of aircraft. No amount of determination or skill could overcome that fundamental disparity in industrial organization. Captured B-17s examined at Tachikawa from 1943 through 1945 were destroyed in the war's final months, either by American bombing or by Japanese authorities eliminating evidence. But lessons those aircraft taught survived in minds of engineers who had studied them so carefully. In decades following the war, Japanese industry underwent transformation more profound than anything attempted during wartime. Engineers who had examined American aircraft and documented American production methods brought those lessons to Japan's post-war reconstruction. They understood that matching American industrial capability required not just copying American products, but implementing American production systems. The transformation required 20 years of concentrated effort. Japanese factories that had relied on skilled craftsmen reorganized around precision machinery and automated processes. Industries that had valued individual craftsmanship learned to value systematic efficiency. Manufacturing that had been organized as collections of skilled workers evolved into integrated production systems. By the mid-1960s, Japanese factories were producing automobiles and electronics using automated production methods comparable to American factories. By the 1970s, Japanese manufacturers had refined those methods, developing production systems like Toyota's just-in-time manufacturing that improved on American mass production techniques. Skilled craftsmen remained valued in Japanese industry, but their role had changed fundamentally. Instead of individually crafting products, they designed production systems and tooling that enabled less skilled workers to produce precisely manufactured products at scale. Precision that had once come from craftsman's skill now came from precision of tooling and equipment. Companies like Toyota, Sony, and Honda became global leaders by combining Japanese attention to detail with American systematic production methods. Quality that Japanese products became known for resulted from production systems designed to build quality into processes, rather than relying on skilled workers to individually craft quality products. In the 1980s, when American manufacturers faced intense competition from Japanese imports, American engineers toured Japanese factories to learn efficiency techniques. The irony was not lost on those who remembered wartime examination of captured American aircraft. The story of Japanese engineers examining captured B17 two-thousandths bombers became a case study in Japanese engineering schools. It illustrated how examining opponents' products could reveal fundamental principles of industrial organization. It demonstrated that success required understanding not just what competitors produced, but how they produced it. Captured B-17s had taught Japanese engineers that modern industrial warfare was won not by superior craftsmanship, but by superior production systems. Not by building better individual aircraft, but by building adequate aircraft in overwhelming numbers. Not by skilled workers, but by systematic processes that enabled less skilled workers to produce precisely manufactured products rapidly. Those lessons learned through careful examination of enemy equipment during wartime became the foundation for Japan's post-war industrial success. The transformation of Japanese manufacturing from craftsmanship-based production to systematic mass production represented the final victory of principles embodied in those captured B-17s examined at Tachikawa. Engineers who had measured rivets and documented production methods in 1943 and 1944 became architects of Japan's industrial rebirth. They had learned by examining aluminum and machinery that modern industry belonged not to those with the most skilled workers, but to those with the most effective production systems. In manufacturing engineering courses today, this story serves as a case study in how examining competitors' products can reveal invisible systems and methodologies. It demonstrates that understanding an opponent's methods matters more than copying their designs. It shows that principles of production ultimately determine outcomes of industrial competitions. The Boeing B-17 Flying Fortress dropped 640,000 tons of bombs during World War II. It earned its reputation as one of history's most effective heavy bombers through combat operations in every theater. But perhaps its most important contribution to history was not the missions it flew, but the lessons it taught when Japanese engineers examined captured examples. Those engineers discovered that American industrial power came not from superior materials or better designs, but from superior organization of manufacturing processes. They learned that standardization, precision tooling, interchangeable parts, and systematic production methods could achieve what skilled craftsmanship alone could not: the ability to produce complex machines rapidly and in quantities limited only by available resources. Captured B-17s examined at Tachikawa Airfield were destroyed more than 70 years ago, but lessons they taught transformed Japanese industry and influenced manufacturing worldwide. Engineers and manufacturers globally learned that mass production and quality were not opposites, but complementary aspects of properly organized industrial systems. The story that began in February 1942 on a muddy Java airfield with a damaged Boeing B-17E awaiting capture by advancing Japanese forces ended decades later with Japan and America as partners in advancing manufacturing technology. Examination of those captured bombers had taught Japanese engineers that their defeat was inevitable. More importantly, it taught them why, and in understanding why, they learned how to ensure that industrial inadequacy would never again limit Japan's capabilities. The Boeing B-17 Flying Fortress served as teacher to its enemies, and they learned the lesson well.